Hello again. This is video lecture 25.2, and we're going to be talking about section 3 in that chapter, where we're going to look at combinations of capacitors in what are called parallel connections and also serial or series connections. We'll start with what's called a parallel connection of capacitors. And we're going to talk about what that kind of connection that is in terms of a circuit by using a circuit diagram. A diagram that represents capacitors and a battery that we will use to charge the capacitors. And the first image on the right is a circuit that shows three capacitors connected in parallel to a single battery. And the way you know they're connected in parallel is that the leads or wires coming out of one terminal, the top one right here for each one, are all just with conducting wire connected together like that. And then separately, the leads or wires coming out of the bottom plate of each capacitor are also just connected directly together with no other circuit element in between them. Now, to charge them up, you then connect that combination to the high and low terminals of a battery to charge them up. Okay? Now, these capacitors that we have are not assumed to have equal capacitance. The one on the right has a capacitance C1, the middle one has a capacitance C2, and the one on the left has a capacitance C3. Okay? All right. So what can we say about such a connection? Well, one of the main things that we have to be able to identify when we see that kind of a drawing, that's a parallel connection of the three capacitors. And that in this case, they've been all connected across the terminals of this battery. And the battery has a job. It creates a potential difference V between its two terminals. That's what it does. Okay, here's the main thing, one of the main things to note. All those capacitors have the same potential difference V, okay, because they are all wired in the way they are. Their top plates all wired together, and then separately their bottom plates all wired together. So they must have the same potential difference across them. That's what the conducting wires are going to do, okay? And because they are connected across the terminals of the battery, that potential difference across all of them is the V created by the battery. And so they show that here with each capacitor. They show V, V, V. Okay? The same potential difference V. But because they have different capacitances, they don't necessarily have the same Q. In fact, if their capacitances are different, they'll have different Qs. We can write down the formula for the Q on each one. For capacitor 1, its charge Q1 will be C1V. For capacitor 2, its charge Q2 will be C2V. And for capacitor 3, its charge Q3 will be C3V. Okay? All right, so they have different Qs, but what they have the same in a parallel connection is the same V potential difference. Now, what we want to do is simplify that circuit down to one equivalent capacitor connected to the battery. And that's what the second drawing shows. Right? It's replaced the three capacitors in parallel with one equivalent one, with some capacitance CEQ for equivalent. We want to be able to calculate that equivalent capacitance. And the trick is to say that the total charge stored on all three capacitors must be the charge on this equivalent one, okay? And the charge on the equivalent one, then, Q, is the sum of the charges stored on the original three, Q1 plus Q2 plus Q3. But then for the Qs, we put in the appropriate C times V for each one that I just wrote down. But then note, they have the same V because they are in parallel, so I can factor it. And then I see that I can just call this sum, C1 plus C2 plus C3, the equivalent capacitance of the single capacitor you see in the second diagram. Okay? And so we can reduce the three in parallel to the one equivalent one, with a total charge Q, that's the sum of the charges on the individual capacitors, and a potential difference V. Okay? Okay, so capacitors connected in parallel can be replaced with an equivalent capacitor that has the same total charge Q and the same potential difference V as the original capacitors. And the way you calculate that equivalent capacitance is right here. CEQ, the equivalent capacitance, is merely the sum of the individual capacitances you had in the parallel connection. Add them up. Okay? Notice then that when you're done, the equivalent capacitance will be larger than the largest of the individual capacitance you started with. Okay? So that's easy, right? You can take a parallel combination of capacitors, reduce them down to one equivalent one, and the equivalent capacitance is just the sum of the individual capacitances. Okay? So capacitors in parallel give you more capacitance overall. They add up. Now, one of the things that people often struggle with is identifying when, given a circuit diagram, you really do have a parallel connection versus, well, not having a parallel connection. So let me draw a circuit diagram, okay, and see if we can talk about whether we have a parallel connection. So there are the terminals of a battery, B, okay? High potential side, low potential side. Careful, the symbol for a battery and the symbol in a circuit diagram for a capacitor look treacherously alike. But notice with the battery symbol, the low terminal side is drawn with a shorter line, and the high potential terminal is drawn with a longer line. Now let's connect some capacitors across this battery. Here's the first one. Notice the lines are of equal length when you draw a capacitor. And that capacitor has a capacitance, let's say C1. And then more wires. There's another one, capacitance C3. And then come down this way, and one more, capacitor with a capacitance C2. Here's my question for you. Are the capacitors C1 and C2 in a parallel connection? I want you to think about that. Feel free to pause the video, get yourself an answer, and then come back. Okay, again, the question was, are C1 and C2 connected in parallel? Answer, no. Why? Because there's that capacitor C3 that has been inserted between the two top plates of C1 and C2. And you can't have another circuit element in between there. You can only have just a simple wire connecting the top plate of 1 to the top plate of 2. In other words, you need just a wire like that. Now, C1 and C2 are in parallel. But if you put another circuit element in between them, maybe it's down here, like that, then C1 and C2 are no longer in parallel. Okay. All right, that's a parallel connection of capacitors. The other connection that's common that we will need to deal with is a little more challenging, is what's called a series connection. Right? If things are in series, there's kind of like an ordered arrangement, one after the other. And that's what we're going to talk about now. So first, now look at the right, look at the top circuit diagram. We have our battery with the high and low terminals and a potential difference V across those terminals. And again, we've got three capacitors with capacitances C1, C2, and C3. But now the way the wiring goes is this. We go from the high terminal lead of the battery into one of the plates of capacitor 1. But then we just take a wire from the low plate of capacitor 1 and connect it to the high plate of capacitor 2. And then a wire from the low plate of capacitor 2 to the high plate of capacitor 3. And then a wire from the low plate of capacitor 3 to the low terminal of the battery. That is called a series connection. And you can just think of that, well, there's capacitor 1, followed by capacitor 2, followed by capacitor 3. Or you can think of it the other way, C3 followed by C2 followed by C1. The order is not so important as the fact that it's just one after the other. Okay? And just connected together with conducting wires, and that's all. Now, what takes a little bit getting used to is the following experimental result. Capacitors in series all have the same charge on their plates. And that's not immediately obvious. The way I'm going to talk about it is a kind of a chain reaction description. Although the ordering is not, it all kind of happens all at once, but I'll talk about it as if it were an ordering. The low terminal end of the battery results in an excess of negative charge, negative Q, on that lower plate of C3. That presence of negative Q on that conducting plate of C3 induces a plus Q on the opposite plate of C3. And then because the top plate of C3 and the bottom plate of C2 are connected by conducting wire, that plus Q on the top plate of 3 induces a minus Q on the bottom plate of 2, which in turn induces plus Q on the top plate of 2. And then because the top plate of 2 is connected by a conducting wire to the bottom plate of 1, that induces negative Q on the bottom plate of 1, which then induces plus Q on the top plate of 1. And all three have then the same Q, even though they don't have the same capacitance. C1 and C2 and C3 can all be different. Okay? And since the C's are different, the V's are different. V1 and V2 and V3 are all different. Okay? Okay, so what's the important thing to note then? Capacitors in series all have the same charge. We'll call it Q. But they have different C's in general, and therefore different V's. But I can say this. The total potential difference across the three capacitors is the sum of the potential differences across them all. Okay? V1 plus V2 plus V3 must equal the V of the battery. So what we can do is we can replace those three capacitors in series with one equivalent capacitance. Okay? The capacitors that are connected in series can be replaced with an equivalent capacitance that has the same charge Q as all of them and the same total potential difference V as the actual series. Let's write down the formulas for those V's. I'll do over the side. I'll just apply Q equals CV for each capacitor. So for capacitor 1, Q equals C1 V1. So V1 is then Q divided by C1. It's got to be true. For capacitor 2, V2 is Q over C2. And for capacitor 3, V3 is Q over C3. Okay? But they have to have the same total V as the battery. So I'll come down here and write that. The V of the battery, I'll write it over here, it's got to equal the sum of the potential drops, potential differences, across each capacitor. So V must equal V1 plus V2 plus V3. But then for V1, I'll replace it with Q over C1. And for V2, I'll replace it with Q over C2. And for V3, I replace it with Q over C3. But they have the same Q. So I'm going to factor. I'm going to write this as 1 over C1 plus 1 over C2 plus 1 over C3, all times Q. And so what we want to do then is replace this blob here with some kind of equivalent capacitance. But in order for the units to be farads, it's going to have to be 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. And then the equation becomes V equals Q over C equivalent. And so we get this rule for calculating the equivalent capacitance for capacitors in series. Notice it's a little different. 1 over C equivalent is the sum of 1 over the capacitances. Okay, and then we're going to have to practice with that, because here's my first warning on that. It's easy to mess that formula up. And here's the sanity check you can use that will often help you if you've made a mistake. When you calculate C equivalent, the number you get in farads must be smaller than the smallest of the individual C's you had to begin with. And if that's not true, stop. You didn't use this formula correctly. Let's go right into a little bit of practice with that formula. I don't think we need practice with the parallel equivalent formula, but the series equivalent formula, maybe we do. So here's a little mini example. What if the 3 capacitors in series have the following capacitances? C1 is 1 microfarad. Just take simple numbers. C2 is 2 microfarads, and C3 is 3 microfarads. What is C equivalent? Well, we use this inverse rule. 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. That's what this formula up here says to do. Add the inverse capacitances for however many you have in series, and that total will be 1 over C equivalent. So 1 over C equivalent is 1 over 1 microfarad plus 1 over 2 microfarads plus 1 over 3 microfarads. And you could just do that on your calculator, but in this particular case, it's not hard to add those as fractions, where the common denominator would be 6 microfarads. Then the first numerator has a factor of 6, and the second numerator has a factor of 3, and the third numerator has a factor of 2. That's 11 over 6. Notice where the units are, downstairs, because what this number is here is 1 over C equivalent. So there's one more key, crucial, final step to get C equivalent. Invert that number you just got. 6/11 microfarad, which is what? A little more than a half of a microfarad. Notice that result, 6 over 11, is smaller than the smallest of the individual C's I started with, which was 1. Right? 6 over 11 is smaller than 1. So capacitors in series end up giving you an equivalent capacitance that's smaller than what you started with. Okay? Now let me give you one more bit of practice, because another thing that people struggle with, like with the parallel connection, is correctly identifying when they do indeed have a series connection. So now let me draw a circuit diagram. Okay, so high and low terminals of a battery. And across those terminals, we're going to connect capacitor with capacitance C1. Then another one with capacitance C2. And then take a wire off here and put a capacitor here. Call that capacitance C3. Question: are C1 and C2 in series with each other? I want you to think about that. Pause the video if you need to, and then come back. Okay, are C1 and C2 in this diagram in series? Did you say no? They are not. Why not? Well, there is a wire connecting the top plate of C2 to the bottom plate of C1, but there's another circuit element also in there, because I've got here what's called a junction of wires, and another wire comes out going into another capacitor. There can't be another avenue for the charge to follow, another path available between C1 and C2. You can't have that there. Then C1 and C2 are in series, like that. But the minute you give the charge another path to take in its motion, like by putting a capacitor like that, then you've destroyed the series connection. Okay? So C1 and C2 in this diagram are not in series. Neither are C1 and C3 in series. But C2 and C3, guess what? They're in parallel. Okay? Okay, so it will take a little getting used to, a little bit of practice, but we need to make sure we can identify when we have a series connection or a parallel connection. And one of the things that the books often do is they give you variations on these circuit diagram pictures that can be confusing. So we're going to end with some class engagement questions that will give us a chance to practice identifying when we have various kinds of connections. So you've got 4 circuit diagrams here. They're numbered 1, 2, 3, and 4. Each one has a particular battery, same kind of battery, and 2 capacitors. Okay, you can think of them as being the same capacitor, it doesn't matter. And you can see the various ways that the capacitors are connected to the battery. The question, which of the circuits have a parallel combination of the 2 capacitors? Okay? Which of those 4 have a parallel combination of the 2 capacitors? And because this is worth practicing, here's another one. Okay? To practice with, also for that same class engagement. Well, we've got our battery, okay? And now we have 4 capacitors, and you can see them labeled there, C1, C2, C3, C4. 2 little questions. In this circuit diagram, are capacitors 1 and 2 in series? That's question A. And then question B, are capacitors 2 and 3 in series? Those are the questions. So practice identifying when we have series and parallel connections, and we'll be talking about this also in class. But that's all for this video.